We're going to do a quick review of electron configurations in the periodic table. If we look at the halogen group, which is group 7A, you will notice that fluorine, chlorine, bromine, and iodine are in that particular order. And if we did the electron configuration for each, and we went to the last energy level and the highest sublevel, you would notice that they are similar in nature, that they always end with the same designation. It's important to understand that all groups within the periodic table have similar physical and chemical properties. That was what modern periodic law told us. And to make it even more interesting, you can see that if we take the highest energy level, I'll do that for each one, and we add up the electrons, you can see that you will always get the same number, 7 valence electrons. And that explains to us why the properties are similar. They behave the same way because they have the same electron structure in their outer shell. Remember that the periodic table can be broken down into the S block, which is groups 1A and 2A, the P block, which is groups 3A through 8A, the G block, which is the group B metals, and the F block, which would be the intertransition underneath the table. Remember, the maximum number of electrons in the S orbital would be 2. The maximum in the P orbitals would be 6 total. The maximum in the D orbitals will be 10 total. And the maximum in the F orbitals will be 14 total. We have two types of elements. Representative elements, which are our main group elements. Those are our group A elements. And remember, those are our towers, groups 1A through 2A and 3A through 8A. They are special in the sense that they exhibit a wide variety of chemical and physical properties, and we'll be discussing the specific family names in the next few slides. And then, of course, we have the transition elements, which are in the middle. Let's give them some specific properties. One that you should already know is that most of those elements have more than one charge. They are typically the least reactive of all the metals. We're going to find that the pattern is metal reactivity is going to decrease as we go across. They are the hardest, densest. They have the highest melting points, and that should make sense. It takes a lot of energy to get them to go to solid to liquid form because of their hardness and their density, and they are great conductors of heat and electricity. All right, let's start off with family 1A, which is called the alkali metal family. They are the most reactive metals. They will always be in compound form. They react violently with water to produce hydrogen gas and a base. Let me give you an example of that. Sodium plus water. Remember, this is an example of a single replacement reaction. The sodium is going to replace the hydrogen to form sodium hydroxide and hydrogen gas. Because these reactions are very exothermic, the hydrogen gas catches on fire and explodes. That's what I mean about reacting violently with water. We find that the alkali metals are soft. You can actually cut them with a butter knife, and they are all silver in color. Because they are so soft, that gives them low density. They have low melting points. It's very easy to get the solid to convert to a liquid. And every one has one valence electron, and by losing that one valence electron, it can form a positive 1 ion. The second family is called the alkaline earth metals. They are group 2A, and they are very reactive, but not as reactive as group 1A. So they will always be found in compound form. You'll never find them free in nature. They also react with water to produce hydrogen gas and a base, as seen in this example right here. Another single replacement reaction. This time we're producing magnesium hydroxide and hydrogen gas. The reaction just doesn't produce enough heat to cause the hydrogen gas to explode. So they're a little bit more safer to use. They are found in ores, which are mineral rocks underneath the ground. And when we are removing the alkali metals from these ores, we would obviously need some kind of chemical process in order to break them from that mineral rock. They are harder, they are higher in density, and they have higher melting points as well. They will have 2 valence electrons in their shell, And when they lose those 2 valence electrons, they can form a positive 2 ion. On the other side of the table, the nonmetal side, we will hit our first family of nonmetals, which are called the halogens, group 7A. They are all nonmetals, like I mentioned. They are the most reactive nonmetals, and once again, when you're very reactive, you'll always be found in compound form. Most of the elements form the diatomic molecules. Remember Brinkelhoff, BRINCLHO, and F. And those guys are basically all right here. At least the bromine, iodine, chlorine, and fluorine are. And if you guys remember, we talked a little bit about how if we go back this way, we'll hit the nitrogen and oxygen. You're kind of forming that 7 to remind us that there are 7 diatomic elements. They have 7 valence electrons in their outer shell. That means that they're all going to want to gain 1 electron for stability to acquire 8 in their outer shell to have an octet, and that's going to form a positive 1 ion. The last group of nonmetals that we're going to talk about is group 8A. Those are your noble gases, and they once again are all nonmetals. They are all gases, and they are non-reactive. That is the key here. They are the most stable elements. They have 8 valence electrons in their outer shell, except for helium, which only has 2. They do not form ions. They do not need to gain or lose electrons because they already have that octet. The last thing that you probably should know is that they're called inert gases. Inert means non-reactive. Last but not least, there are a couple of other important areas of the table. Of course, we know hydrogen is misplaced. It is a nonmetal. It really should be on the right-hand side. It can take on a +1 charge, like the alkali metals of its group. Some periodic tables put it over here. It can take on a -1 charge, like the halogens of that group. Some tables actually put it in the middle because of the fact that it has the ability to be plus or -1 in charge. And the inner transition elements, which are down at the bottom, have names. The first row is called the lanthanides. And you'll see in the table that lanthanum kind of starts that row of special elements, which are called rare earth metals. There really isn't much I want you to know about these except for its nickname. And then the last row in the lower block are called the actinides, and that will start right here, AC. And the only thing that you need to know about these guys is that they are all radioactive, and most are man-made, meaning that they've been created in a laboratory, probably through nuclear reactions.